The rigid tables of traditional relational databases are failing. When subjected to massive, unpredictable streams of modern, unstructured data, those strict rows and columns simply shatter under the volume. The necessary evolutionary step is NoSQL. NoSQL, which stands for Not Only SQL, is a category of databases designed to handle varied formats by scaling out across multiple servers. But treating NoSQL as a single, uniform replacement for your old database is an architectural trap. To evaluate these systems correctly, we rely on the framework developed by Royal Research in their definitive guide to leading NoSQL database architectures. The stakes here are high. Selecting a database based on brand name or market popularity, rather than its structural compatibility with your specific application, guarantees crippling technical debt and forces expensive, ground-up system rewrites later. This quadrant chart reveals the two critical axes you must evaluate. On the x-axis, we measure the complexity of your data structure, ranging from simple flat logs to highly connected webs. On the y-axis, we measure your scaling requirement, from a single local node up to a globally distributed multi-data center deployment. The four major NoSQL architectures, document, column family, key value, and graph, each occupy a very specific, optimized territory within this matrix. If you fail to match the specific structural strength of a NoSQL database to your application's primary bottleneck, your infrastructure will fail. MongoDB leads the category known as the document store. As this diagram illustrates, it uses a schemaless, JSON-like document structure. JSON is a lightweight, text-based format that stores data in flexible key-value pairs rather than rigid tables. This means the database seamlessly absorbs evolving data inputs without predefining the structure. That flexibility translates directly into developer agility. Engineering teams can push application updates and change data requirements on the fly, without halting the database to restructure entire tables. To handle immense scale, MongoDB utilizes a process called sharding. Sharding horizontally partitions data across multiple independent machines. By dividing massive datasets into smaller, manageable chunks across distinct server nodes, the system maintains high availability and fast query performance even as volumes explode. The trade-off for this freedom is discipline. Because the database itself does not enforce strict relational rules, your application code must rigorously manage data validation to prevent inconsistent or orphaned records over time. MongoDB is the optimal choice when your business logic prioritizes dynamic evolution and structural flexibility over strict pre-planned data conformity. Apache Cassandra is built for a different extreme. It is an enterprise-grade column family store. This diagram shows Cassandra's defining feature, a peer-to-peer node architecture. Unlike traditional master-slave setups, every node in this ring is identical and capable of handling read and write requests independently. Without a central master node creating a bottleneck, Cassandra achieves linear scalability. You can distribute petabytes of data globally with 0 single points of failure. If hardware fails or a disaster strikes, pathways instantly reroute to surviving nodes, maintaining continuous system flow. The operational trade-off for this geographic resilience is eventual consistency. Eventual consistency is a database model where data updates take a brief moment to synchronize across all nodes, meaning different users might temporarily see slightly older versions of the data. That slight delay disqualifies Cassandra from running systems that require millisecond-accurate transactional ledgers, like a banking application processing simultaneous wire transfers. Cassandra intentionally sacrifices immediate global synchronization to guarantee continuous, unstoppable uptime for massive data ingestion. Redis serves the performance optimizers as an advanced key-value store. Its defining trait is that it stores data entirely in memory, using RAM. RAM is a computer's volatile, short-term memory module, which allows data to be read or written at exponentially faster speeds than a physical hard drive. Bypassing the mechanical friction of disk I/O unlocks sub-millisecond latency. This extreme speed makes Redis the industry standard for real-time analytics and high-volume event messaging. The limitation is entirely financial. High-performance RAM is exponentially more expensive per gigabyte than standard disk storage. Managing true big data volumes in Redis requires deploying complex persistence strategies and data sharding. Without careful configuration to balance memory usage and data size, server costs will quickly overrun budgets. Redis forces a clear compromise. You trade cheap, infinite storage capacity for unmatched real-time data retrieval speed. Neo4j addresses a problem the others cannot solve. It is a native graph database. Watch how these traditional, flat rows transform. Neo4j discards tables entirely in favor of a native node and relationship structure, storing the data points and the exact connections between them as equal entities. This architecture permits instantaneous traversal of highly connected data networks. It powers complex pattern recognition for AI engines, social analysis, and fraud detection. Instead of scanning the entire database, it simply traverses the direct path between nodes, returning deep insights in milliseconds. Now, the core trade-off is structural overhead. Graph databases are highly inefficient if you are simply trying to store massive logs of disconnected linear data. If the relationships between your data points are irrelevant, Neo4j is more valuable than the individual data points themselves. Choosing a NoSQL database means choosing the specific survival trait your application requires to function. This decision flowchart, based on the Royal Research NoSQL Architecture Guide, maps out the exact deployment path for your needs. For the agility-seeking developer who needs to build rapidly evolving applications with varied data types, the path leads to MongoDB. For the enterprise architect who requires massive scale and extreme multi-region fault tolerance, the path leads to Cassandra. For the performance optimizer, demanding immediate data retrieval and real-time processing, the path leads to Redis. And for the relationship mapper, prioritizing deep pattern recognition and interconnected data, the path leads to Neo4j. To explore the deeper technicalities of deploying these platforms, read the full Royal Research Guide linked below. Objectively matching your database architecture to your specific operational constraints is the only true foundation for scaling a modern application.